It is my pleasure to introduce today's presenter, Parag Salva. After starting his IT career as a student network technician at the University of Maryland, Parag learned enough for his first job out of college as a network administrator. For several years, he took on progressively advancing roles supporting numerous commercial, government, and DoD networks. In addition to gaining valuable experience, he also earned certifications from Novell, Microsoft, and Cisco. He has been teaching with Global Knowledge since 2000, including CCNA, CCNP, VoIP, and BGP courses. Parag, it's all yours. Let's begin.
Okay. Thank you very much, Jim. Welcome, everybody. So what are we going to talk about here? We basically are going to talk about the basics or the foundational knowledge for networking. And as far as the list of topics, we're going to first answer the question why this is so important. Then we'll talk about the OSI model. We'll talk about switching, routing, and finally TCP/IP and subnetting. And then we'll, of course, have some time for question and answers. So first of all, why is this important, right? I always like to ask the question, why do I need to know this? And the basic answer is without this foundational knowledge, it's virtually impossible to design and operate or manage the networks or even troubleshoot them. Excuse me. So all of these fundamental functions that we need to perform for all the networks can't be done without the basic knowledge. Right? So that's the idea. So one of the first things is the OSI model, right? What is it good for? What is it used for? The idea is that the OSI model breaks up the entire networking process into manageable functions, manageable pieces, and distributes them across these 7 layers. Right? So it distributes them across these 7 layers. And the idea is that, excuse me, sorry. The idea is that it also is a great learning tool. So not only do vendors use this to design their products for the appropriate layers to perform the right functions, but you and I can use this as an incredibly valuable tool to just learn about the networking process and how the various functions are associated with the various different layers of the OSI model. Now, if you as a networking professional need to learn more about this, it's very important to know not only the names and numbers, but literally all the various functions associated with each of the layers. We need to also understand the various protocols, the various devices, the various standards associated with the various layers of the OSI model. Right? So that's the idea. Now, the bottom 3 functions, the bottom 3 layers, layers 1, 2, and 3, are performed typically using hardware. The upper layers, and sometimes transport layers also called the lower layers, but 4 through 7 layers are performed. The functions associated with those are performed through basically the software, right? So it's more in the programming, if you would. Now, how is this going to work? Let's pretend that there's a sender of some data here on the left and a recipient on the right. Yeah, the idea here is that when that sender, let's assume sending an email to a recipient. So when they do that, then what's going to happen is basically as soon as they click on the send button, their device will kick off the process of this communication, and each of the layers is now going to add instructions by way of the headers. Information and instructions are included in these headers, and eventually, and each layer will add its own header, if you would. Eventually, the data is going to be transmitted, on the wire or wirelessly as 1s and 0s, as bits, and then the recipient device will process these headers, use that information, and then eventually will basically determine which application or which process to send the data to, and it will eventually show up in the right window or the right process in the recipient's machine. Now, and that's, for example, if it was an email, that's when the recipient will get a little ding that says you've got mail. Right? So that's the idea here. Now, we'll talk about some of the layers, not all of them, but physical layer defines the actual properties of the actual connection. including things like if it's a wired connection, how thick is the cable, how long can it be, what is the connector type on the cable, and even the electrical signals. So whether it's copper-based cable or fiber optic-based cable, or if it's wireless, how are the actual signals being transmitted? What kind of electrical or light signal or what kind of a radio signal is being used to communicate a 1 versus a 0? All of that is defined by the physical layer. Data link layer, layer 2, is one of its primary functions is to provide the MAC address, sometimes called the physical address, MAC address, sometimes called the hardware address. Right? All of those are the same names for the MAC address, and that MAC address uniquely identifies each individual device. It's typically burnt in or coded in by the vendor or manufacturer of the device. The data link layer also specifies who can access the media when. So media access control, right? Who can transmit when and so on, is also defined by the data link layer. Most switches operate at the data link layer because they use the MAC address to perform their primary function of forwarding data. And so most switches operate at the data link layer. There are some switches that operate at the network layer as well, but I'll talk about that later on. So these are the layer 2 functions, data link. Ethernet, by the way, the traditional wired Ethernet, that actually operates on both the physical and the data link layer. Okay. So, excuse me. So the basic the idea here is that the Ethernet spec operates at physical and data link layer. That's just one standard. There's lots of other standards. Wi-Fi also operates at physical and data link layer and so on. So that's the idea here. Now, let's see here. Yeah. Network layer. What are its functions? Its functions are to provide the logical address. Yeah. Logical address is called that because that's something we assign. The MAC address is assigned by the vendor. Logical address is assigned by us. And so, you and I, as network designers or administrators, are going to assign addresses to devices. And then we also, the other function associated with the network layer is routing. Literally, the decision of how to forward the data to the appropriate destination is performed by the network layer. And then prioritization, sometimes called quality of service, determines which data is to be processed first or given higher priority over others, and so on. So all of these functions are performed by the network layer. And again, a standard that exists at the network layer is IP, right? In the TCP/IP protocol suite, IP is quote unquote the main protocol that operates at the network layer, and it helps us with the addressing and routing and whatnot. Transport layer, one of its functions is to segment the data. If you and I were watching a large YouTube video over the internet, then the transport layer will break up the video into smaller packets first and transmit each of the packets, and then also maybe help with error handling. If one of the packets gets an error, potentially then the recipient might say, look, I got this packet, but it has an error, so can you please retransmit it? So then the packet is retransmitted by the sender. And one of the other big functions of the transport layer is to identify what protocol, what application, or what process the data should eventually go to. That's why, because on a single machine, we could be using lots of different applications like email, browsing, instant messaging or chatting, database applications, etc. If all the data is coming in over the same connection, whether it's Wi-Fi or wired connection, eventually our machine has to figure out which application to send the data from each individual packet to. And that function is performed by the transport layer. The transport layer identifies, oh yeah, send this packet to the email, send this packet to the browsing session, send this packet to the chat session, and so on. Right? So that's what's important. And of course, the main protocols today that we use for transport purposes are TCP and UDP in the TCP/IP protocol suite. So that's the OSI model, if you would. And again, we won't get into the upper layers right now, just in the interest of time, but it's important to understand those as well. I just wanted to highlight some of the layers and how we want to think about it, right? So, and usually layers 1 through 4 are more involved in transporting the data from device to device and within the device. The upper layers functions are still important, but not quite as critical to understand. Now, I like to think of the switch as the equivalent of Uber or a regular cab, if you would, or even the shuttle service that we use. The switch gets our data from one device to another device. From device to device is what the switch does. And its purpose is to handle local traffic, as opposed to what? Remote traffic, which is what routers perform forwarding of. So the switch will do a job of forwarding local traffic using 3 main functions that it performs. So one of the first functions is it learns. Now learns what? Learns MAC addresses. It learns MAC addresses so that it can perform its job much more efficiently. And again, we'll get into some of the details in a moment. It learns MAC addresses so that it can forward and filter efficiently, and it's not forwarding data to everybody, only forwarding as appropriate. And flooding as well, I'll talk about in just a moment. Right? So flooding means, the term flooding, by the way, is different from broadcast. Students often make mistake of confusing flooding with broadcast. Broadcast means, by definition, that packet is meant for everybody. Whereas flooding means it's being sent out all ports of a switch, but it's not necessarily for everybody. It is being sent out because, and one of the reasons that flooding is done is when a switch does not know who to really forward it to. So it's so, yeah, I don't know, let me forward it to everyone. And so that's called flooding. But that's different from broadcast, which is basically, it's addressed to everybody. So how does the switch operation, or how does the switch perform its functions? Let's take a look. So here we have a switch with 4 ports connected to 4 different PCs. And each device has its own MAC address, if you would, that's unique. The MAC addresses have to be unique worldwide, ideally. At least within a single network, they have to be unique. And each switch maintains what they call a switch lookup table or a MAC address table. This table goes by various names. And so the switch lookup table, MAC address table, sometimes in the Cisco world, they call it the CAN table. So assuming a device has just, a switch, sorry, has just booted up, its MAC address table might be empty at first. So when device A sends out a frame, the switch will first examine the frame's source MAC address and then add that to its switch lookup table, saying that I just received, the switch says, aha, I just received a frame on my port 2 with this source MAC address. That means this source MAC address, or this device with this MAC address, lives on my port 2 because it's talking from there. And so add that to its switch lookup table. And when it does, now it can basically, next time it receives a frame for this MAC address as a destination, it will know that, okay, I need to only forward it out port 2, nowhere else. But right now, the frame's destination MAC is this, which is actually corresponding to C's MAC address. But the switch does not know it. The switch lookup table does not have the destination MAC address in its lookup table. So what is the switch going to do? The switch is now going to flood it. So it's, I don't know where this destination lives. Let me flood it. Let me send it out all ports. Now, of course, that means B, C, and D, all of them will receive that frame. And both B and D will say, whoop, that's not our MAC address, throw it away. And they discard that frame, ignore it, or they throw it away. C says, whoa, that's my MAC address. I better pay attention, and I better open it up and process it. So C will basically process that frame, and ideally, in an ideal network world, C will respond. Now, when C responds, right, when C responds, what's going to happen is the switch will once again say, aha, I just received a frame in on my port 7, which is what C is connected to, with this source MAC address. So the first thing it does is it adds that source MAC address to its switch lookup table and associates that MAC address with port 7. That says what this MAC address lives on my port 7. Now, of course, bear in mind if the human, if you and I, move that device C from port 7 to port 8, the switch will eventually update its MAC address table very quickly. As soon as C sends out another frame, switch says, oh, look, looks like that MAC address has moved from my port 7 to my port 8, so it'll update the MAC address table to reflect that change. And in the MAC address table, each MAC address can only be associated with one port. A single port can have more than one MAC address. If you've got another switch connected to that port, then obviously it'll have lots of MAC addresses. So that's the idea. However, now the switch will look at the destination and say, aha, I know that this destination lives on my port 2, so I will only forward it out port 2 and filter on all the other ports. Right? So it basically sends it out only on port 2, forwards on port 2, filters on the other. That's what they mean by that. And of course, as you saw earlier, it'll flood a frame if the switch does not know where that MAC address lives. Right? So that's the idea there. Now, one of the other big things I want to point out is it'll also flood out broadcast. By definition, a broadcast will have the destination MAC address. Let me just, instead of this as the destination MAC address, the destination MAC address will be all Fs, which indicates it's a broadcast. And usually some source does not know who to really send it to. They send it out as a broadcast. Something inside that frame, though, will determine which device it's actually meant for. But at first, it's the device that's sending it does not know, so it sends out as a broadcast. That, too, will be flooded. One of the other big problems with switch networks is loops. Now, the thing is, as you and I, as administrators or designers of the network, we would want redundancy. But the problem is anytime we introduce redundancy, we introduce loops. And when we introduce loops, then basically that creates a lot of problems, a lot of confusion. So spinning tree protocol is on by default on all switches. And its purpose is to break the loop so that it logically appears as if this link is not working. It blocks this port so that this link appears blocked, and that means it's just not operating normally. There is no loop, so to speak, right now. But if the other link gets broken, any of the other links gets broken, then this link will be as a port, and then the link will be unblocked so that the data can flow through this and that the redundant connection can be actually used. So I could talk for a day and a half about spinning tree protocol. So obviously we're not going to get into details today or right now, but you could learn a little bit. It's very important to understand some of the basics of that as well. Now, remember I said switch is like the Uber or the local cab or the local shuttle that gets me from my house to the airport. Well, routers are like airlines, and routing is getting the data from one network to another network. Remember, the airline does not care how we get to our house or our family or friend's house or the hotel we are going to. The airline only cares to drop us from one airport to another airport with our luggage more or less in one piece, right? And so the idea here is that routers help our data get from one network to another network. But within the network, how to get to the right device is the switch's job. Router's job is to get us from one network to another. They figure out the best path to get our data from one network to another. So literally when you and I type in www.amazon.com, routers, lots of routers in between Amazon and us are figuring out how to get the data, our request to Amazon, and how to get the Amazon web page and all the data from Amazon's website to our machine. That's what routing is all about. Right? So it's important to understand several things about routing. And it's so complicated. The thing is we don't appreciate how complex and how sophisticated and how fast this is just because today we don't need to. It's just like we don't need to understand how a car's engine works just to be able to drive it. We just push on the gas pedal and we go, you know. Similarly, we just type in www something and it just works. But underneath the hood, there's a lot of stuff that's going on. And as network professionals, we need to understand some of that. So the first thing is the routing decision process. When a router receives a packet, how does it figure out how to forward that packet, right? Because remember here, you have lots of different paths. The router has to make a decision. For example, this router here at the bottom has to make a decision of do I send the data out this way, or this way? And that's what this decision process is all about. So each router has a routing table. Now, I won't tell you yet how it's built, but the routing table has a list of all the routes, all the destinations that the router knows about. And so every time the router receives a packet, it checks its routing table to see if there are any matches between the packet's destination address and the routing table, and the routes in the routing table. So if the router can find one match between the packet's destination and a route in the routing table, if there's only one match, no more, no less, then it's easy. The router says, okay, it's just one match, use that route and send the packet on its way to wherever the route is saying it should go. So that's easy. Whereas if there are no routes matching, then the router also says, okay, that's easy. I don't know how to get this packet towards the destination at all. And by the way, routers at that time are not going to try and figure out how to send this packet. The router says either I know or I don't. If I know, I'll forward it however I think is the best way to do it. If I don't, guess what? That packet gets dropped. That packet gets discarded right away. Why? The router says, I'm busy. I've got millions of packets I need to be processing per second. So I don't have time to fool around trying to figure out, well, I don't know, let me ask my buddy. It doesn't do that. It just says, nope, don't know, sorry, boom, crashes the packet, and then immediately sends a response back. Or usually, not always, but usually sends a response to the source. Whatever address was in the source address of the packets, then gets a response saying, look, I don't know, I didn't know how to forward your data. I don't know why someone thought I would, but I didn't know, so I had to discard the packet. Sorry, kind of. That's kind of what it's saying. The third option is if the router has multiple routes that match that packet's destination address with its routing table. Now, when multiple routes match with the packet's destination address in its routing table, then it gets a little bit more complicated. Now it has to find the best match, and it tries to match the maximum number of bits, in the address, in the packet's destination address and the route address. It tries to match the maximum number of bits. That's called the longest match, and that's what's used to forward the data to the destination. So all this gets complicated when routers are processing millions of packets per second, and they have thousands of routes in the routing table. So that's when it gets more complicated. On very simple routers like our home Wi-Fi routers, it's not that complicated. But in our large companies and large enterprises network, this stuff gets complicated. But routers today are built to be able to built to be able to handle a very large number of packets very quickly. And that's why they cost so much, these routers, right? It could easily cost a few $100,000. Now the routers, one of the criteria the router uses to figure out which is the best path is called a metric. Metric is nothing but a term used to describe basically a measurement, some kind of unit or measure of how easy to reach or hard to reach that destination is. And so the idea here is that there are various different types of metrics. Hop count is the least sophisticated. It just says how many routers do I have to send the data across to get to that network, which is not very sophisticated. Bandwidth is much more sophisticated. It says, okay, let me measure the bandwidth of each link, and then I'll add up the cost of each, or the bandwidth of each link, and figure out the bandwidth of the entire path, and I'll choose the path with the best bandwidth. Similarly, we can arbitrarily assign a cost, kind of a numeric or a monetary cost, to each link of the path and then the router will pick the path with the lowest cost. So that's fairly logical as well. Reliability, delay, and load are also potential metrics, but they're not as useful. So those aren't used as commonly. Usually bandwidth and cost is used more commonly. Hop count is used in simpler routing protocols. But at the end of the day, guys, here's one of the big things. Remember I mentioned the routing table and the routing decision process? Think about in this network, most of these routers will know multiple ways to get from one network to another. Guess what? When these routers have learned about multiple ways to get from one network to another, only the best path information is sent to the routing table. The routing table only has the best path information. Well, you say, what about the other paths? The other paths are in the router's back pocket. Now, the other paths are in the router's back pocket so that it can use them if it needs to. If the best path is not available, it'll choose the next best path, but only the best path is used, and that's what's put in the routing table. Now, routers use routing protocols to figure out which is the best path, and that information then is sent to the routing table. So the routing protocol, in a sense, and by the way, it's very, very important you understand the difference between routing protocol and the routing process, or the routing decision process. The routing protocol is what routers use to talk to each other to figure out which is the best path, which is not, or what's the cost of each link, and so on. So notice to go from lane A to lane B here, there are various different paths. But if we use hop count as the metric, if hop count is the metric, then guess what? The bottom path is the fastest, or the best. I shouldn't say fastest, but the best because it has the fewest number of hops. You only have to go through 2 routers to get between lane A and lane B. Whereas the top path, or I wouldn't say top, but the gigabit links path, is 4 hops. So routing protocols that like RIP, that uses hop count as its metric, will think, oh, that path is very inefficient. Whereas look at the bandwidth. If you use bandwidth as the metric, then like OSPF and EIGRP typically use, then the gigabit link path is the best because it has much higher bandwidth than the 10 megabits or the 155 megabits. Right? So that's the idea. So routing protocols is what routers use to talk to each other to figure out which is the best path, what is the cost of each path, and so on. And then, based on that knowledge, based on that information, the best path information is sent to the routing table. Right? So that's the big thing about routing. Now, of course, routing, again, is also very complicated. There are lots of options, lots of other details you have to think about. That's why I could, again, talk about routing for 5 days, right? Including the various different protocols and how the details of those protocols are used to determine the best path and whatnot. The operations of each of the protocols as well. The other huge thing we need to know as networking professionals is just what is TCP/IP. TCP/IP is basically the protocol suite of lots of protocols. These are just some of them, right? Lots and lots of different protocols are used in TCP/IP. Some of these are called the core protocols. So most of the protocols being displayed on the screen here are called core, as in all devices that claim to have TCP/IP functionality have to have support for these. But there are hundreds and thousands of other protocols in TCP/IP, not all of which may be used. And at the heart of TCP/IP, of course, is IP, right? Internet protocol. All our data, really, whether at home or at work, typically is riding in IP packets. That's why it's so critical that we understand even IP as a protocol. And then TCP and UDP. So IP operates at the network layer. What they call internet is the network layer. What they're calling network access is layers 1 and 2. Ethernet, Wi-Fi, etc. operate there. IP operates at the network layer, and excuse me, TCP and UDP operate at the transport layer, and these are application layer protocols. So again, lots of different ones. But again, it's very important to understand how these interact with each other, how they operate within themselves, the details of these protocols is very crucial for us network professionals to understand, to be able to troubleshoot, design networks, and so on. Yeah? And of course, then the IP addressing, right? And we are talking about IP version 4 here, of course, not version 6. IP addresses are 32 bits long. Now, we typically write them in what is called the dotted decimal notation. This is what an IP address looks like. But if you ask me, why, what is the IP address of your PC? And if I start reading it out to you in binary, because it's 32 bits, they're going to complain. They're going to say, hey, Parag, stop. Knock it off, right? I can't handle if I start reading 1100, blah, blah, blah. I can't deal with that. So you would want to hear that as 172.16.200.1. But basically, each 8 bits is converted to decimal, separated by dots. That's why it's called dotted decimal. And of course, so here it is, right? 4 octets being divided into, or the 32 bits being divided into 4 octets, as it's called. And each octet converted to decimal, separated by dots, makes it the dotted decimal notation. So this long string of bits, which is ones and zeros, is really represented by 192.168.10.100. Right? And now, at the end of the day, guys, we have to subnet our addresses. Now, what does subnet addresses mean? Subnetting basically is taking up one large network and breaking it up into multiple smaller subnets. Most of the addresses have a network portion and what they call locally administered or host portion. So you have a network portion, a host portion, a third portion is created called the subnet. Now that's something we have to do usually. And not all of us, of course, but those who are designing the network, those who are assigning addresses will have to create subnets. And when we do that, we basically, first of all, the question is why do it? So first, the answer is to make the networks more manageable. Otherwise, it becomes impossible to manage them if they're so huge, right? And the other is to reduce address waste. Without subnetting, we waste a lot of addresses. Now, again, if it's not clear to you why or how that address is wasted, it's a little bit longer discussion than we can get into in this webinar. But certainly when I teach classes associated with these topics, I spend 4 hours or more teaching subnetting. And that's where we get into the details of how it reduces address wastage and whatnot, right? So the things we often have to ask ourselves is how many broadcast domains or how many networks are we trying to create? Within each network, how many addresses will we need? In other words, how many devices, PCs, routers, switches, printers, servers, etc. will we have within each network? What is the total range of the addresses and also the potential for growth? Will that network grow in the future? Do we need to account for some growth and add extra addresses so that we are not having to redesign this too often? Right? So that's the idea. Now, in order to actually understand the subnetting part of it, that's what gives students a lot of heartburn, a lot of difficulty, because what happens is students try to do subnetting without understanding all the basics. Now, there's a lot of basics that need to be understood first in order to do the quote-unquote subnetting or the actual math. The first thing is you should understand very clearly why we need to do it. That's what I just described, right? The goals are. Again, you need to understand in a little bit more detail than I'm sharing here, but how does it make the network more manageable and how does it reduce address wastage? So that's the first thing. Second is the binary numbering system and conversion. You and I need to be able to convert this binary string to 192 back and forth. And it's not important to be able to do it very quickly, but you should be able to do it even without a calculator, by the way. When I, again, teach subnetting, I insist that students be able to do it without a calculator. It's okay if you're slow at first, but it's important to know how to do it. Otherwise, you won't really understand subnetting. So the conversion of binary to decimal and and decimal to binary, both ways. It's also important to understand the IP address classes and octet boundaries. The classes A, B, and C primarily. Also, the subnet mask must be understood and the rules associated with subnet mask. So that's very critical as well. And also, when we have network bits and host bits, just like here, you have network portion of the address and host portion of the address. Or like here, you have some portion of it is the network, some portion of it is the host, and so on. Well, you and I have to be able to count how many bits are the network portion, how many bits are the host portion, and how, depending on how many bits we have, how many addresses or subnets we can have. So all of that has to be figured out. And again, if you don't understand that relationship between the number of bits and number of hosts or number of subnets, excuse me, that won't be clear how to do it. And we have to be able to count the bits, right? The network portion, subnet portion, host portion, and even the prefix notation. Sometimes you'll see a mask written as a /16 or /24. It's important to understand what that really means, what that number really means, the significance of that. And the analogy I like to use is, subnetting is like slicing a pizza. Whenever we order pizza, it always comes sliced. And so think of the address of the original network, unsliced pizza of 172.16.00/16, right, before subnetting. And once the pizza is sliced, now you have an address of the slice. So for example, 172.16.5.0/24 might be the address of one slice after subnetting. Another slice might be 172.16.6.0 and so on. So that's really the gist of basically how subnetting works. And this is, like I said, this is the analogy. Once the pizza is sliced, by the way, the original pizza is not in its original form anymore. So it's the same way with subnetting. Once you subnet, the original network is not in its original form anymore. Now we only have subnets. And this also can get a little complicated. Students often are afraid of the math. And that's why I actually, like I said, spend at least 4 hours teaching this, because I insist that students know all of this first before they do a single subnetting problem. So this takes a while to make clear and to explain, but that's the idea. And then, of course, the beauty is once you understand all this, subnetting becomes very easy. And it actually becomes fun and easy, because now it's not something we are troubled with. We don't find it difficult, in other words. But without the basics, if we try to do that, guess what? It just doesn't work, guys. That's, again, one of the other big reasons I emphasize on all these fundamentals, not only the OSI model, switching, routing, TCP/IP, and subnetting. Right? I emphasize all these concepts in the class, and I tell students, look, if you really want to understand it, be really clear about the purpose, the definitions, and then things fall in place. Then you get really good at designing networks or troubleshooting networks. And it's not something it won't stress us out. We won't be anxious about that. We'll view it as a good opportunity or a challenge and figure out and solve a problem. So that's really the gist of it. So I always like to use a lot of humor in my classes also, and so I thought I'd share a few what some people might call dad jokes or groaners. But what I like to call just as some jokes, something to make you smile. Take a look, see what you think, and then we'll get into question answers. I'll give you guys maybe 30 seconds to read this, and then we'll continue on. Some of these you may not understand, but if you've been around networks or done networking, then some of these will give you a smile. All right, so questions. I think you guys have a question box. You can put questions in.
Hey, Parag. Thanks for that. Great presentation, great session. We have a ton of questions. So we have about, let's see, 20 minutes left over. So we'll see how many of these we can get through. I bet we'll get through most of them. So I'll just read them out to you, Parag, and you can answer them as best as you can, and we'll see how far we get. First question is, what is the difference between a frame and a packet?
Outstanding question, by the way. So And really good question, because it's important to know the distinction between them. The frame, whenever the term frame is used, it's referring to layer 2. When a packet is mentioned, it's referring to layer 3. Now, bear in mind, these terms are often used very, very inappropriately. As in, when people, networking professionals, are talking about these, they'll often use one term when they mean the other. But generally, when we say frame, we are referring to layer 2 at that point. So the focus is layer 2. And by the way, a packet contains a frame. So, in some sense, and by the way, I'm guilty of that too sometimes. But I'll always clarify to students that right now it doesn't matter. But when it does, I'll make sure I'm very clear about the difference. So frame brings into focus layer 2. The layer 2 header is what we usually look at, like Ethernet, for example. When we say packet, we are looking at layer 3 header, network layer. So at that time, it's an IP packet, if you would, versus Ethernet frame. And so that it brings into focus different aspects of that unit of data. By the way, just to extend that idea further, at layer 1, at the physical layer, the unit of data is bits, just like ones and zeros. And at the transport layer, it is segments, or datagrams, as it's sometimes called, but segments or datagrams. And so frame is layer 2, packets layer 3. Think of that. Thanks.
Yep. Thank you, Parag. Next question. Let's see. If the switch powers on, how does it update the address table to know which device is connected to which port?
Excellent question. When a switch powers on, the MAC address table is empty, or it has a few addresses which are static or fixed or whatnot. But it literally waits to hear packets. Now the problem is, I shouldn't say problem, but the good thing is that these days our machines are so chatty that they're constantly sending stuff. And so it doesn't take switch very long to learn MAC addresses, because as soon as it starts receiving these frames from the various ports, it'll start adding these addresses to its MAC address table and builds its MAC address table that way. Which is also why when we move a device from one port to another, it won't take very long for the switch to update its MAC address table either. So it's not like we can fool the switch into thinking, aha, let's see if you can keep up. Well, the switch can keep up much faster than we can, right? So that's how it happens. Yeah.
Great, thank you. Let's see, would an email sent to all in a company or department be considered a broadcast? And all was in quotes.
Got it. Really good question as well. By the way, all these questions so far are outstanding questions. I mean it sincerely. I'm not just trying to flatter you guys. This is what I encourage you guys to always do, ask questions. So the broadcast term also has relevance. It applies at different levels. You can have a broadcast at layer 2. You can have a broadcast at layer 3. And the email is a broadcast, so to speak, quote unquote, at layer 7. Because it's addressing all the email users. Now, the email users are not, so to speak, associated with the OSI model layer, except you can think of it as an application layer broadcast, if you would, right? But layer 2 would be an Ethernet broadcast. Layer 3 would be an IP broadcast. And an email broadcast, think of it loosely as a layer 7 kind of broadcast. Although I say that with a little bit of hesitation, but I hope you get the idea. But the term broadcast does apply across numerous layers as well. Good question.
Great, and thank you. Let's see, next question. When you say switch lookup table, do you mean ARP table?
Very good. No, those are different. ARP, in fact, let me go back just to show you. Take a look right here. ARP is separate. ARP is a TCP/IP protocol that associates the IP address with a MAC address. Right? So it's a separate protocol. I don't want to get into it more right now, but just know that that's totally different. The switch MAC address table is a layer 2 function only, whereas ARP table is really, it operates between layer 2 and 3 because it's associating the IP address of a device with the MAC address of a device. And each TCP/IP device, not just switches, but PCs, switches, servers, routers, all have ARP tables. let's say if I want to send a packet to this IP address, what is the MAC address I will use also, right? So that's the idea, but yeah, so it's definitely different. Yeah,
Perfect.
go ahead, Jim.
And I'm not sure if this one's a question or a recommendation for a rap song. All it says is WAN can root question mark.
Whoa, I'm sorry, repeat that, please.
WAN, W-A-N, can root question mark. So R-O-O-T.
Yeah, I don't want to say anything because it's not clear to me. Yeah, sorry.
Okay.
Have them clarify it. If they can clarify it, I'd be happy to address it.
Yep, if that person wants to repost that question with a little bit more information, we'll get it covered. Let's
Great.
see, which is the best routing protocol with the least or with minimum failures and maximum routing process?
Okay, so if you ask Cisco that question, they'll tell you it's EIGRP because it's a Cisco proprietary protocol. Now, Cisco is a giant, right, in the networking world or the routing world especially. But in my personal opinion, and not just my opinion, but you know the industry standards, so to speak, EIGRP and BGP. I apologize. EIGRP and OSPF are the two leading protocols in most networks. So, and EIGRP and OSPF both are very good. They're both very fast. They're both very scalable. They're both very accurate. It's hard to fool them. Yeah. Whereas RIP, by the way, the first routing protocol that was developed didn't scale well. It couldn't scale to large networks. It was very easy to get confused. And so it would create loops and whatnot. But the answer to your question, you can't go wrong with either OSPF or EIGRP. OSPF is standards-based. EIGRP is Cisco proprietary. But yeah, and those are the ones that are, in fact, most of the networks will use one of those two.
Great, thank you. Let's see, next question. Please explain the significance of /16 and /24.
Oh, well, let me see if I can give you a Reader's Digest version. The /16 or /24 is referring to how many ones there are in that mask. That's really what it is. You have to count the ones now, but it could mean different things depending on how and when it's used. Because there's subnet mask, there's network mask, and it's also used to denote or signify sometimes other ideas as well. Yeah. But yeah, so the idea there is that it's basically, oh gosh. Let's see here. Oh, by the way, Jim, can you hear me?
Yes, I can. You sound perfect.
Okay, sorry, because I've got something on my phone that indicates that the call was dropped, but okay. Sorry about that. So the question is, let's see here. The question is, you know, depending on how and what the context is in which it's used, it'll vary a little bit. But for a subnet mask, it is /16 means there are 16 ones in it. That's indicating the network and subnet portion. /24 means there are 24 ones in the mask. That's indicating again, the network and subnet portion. /16 is written as 255.255.0.0, whereas /24 is written as 255.255.255.0. I hope that helps. That's the Reader's Digest version of the answer, by the way. To give you a thorough answer will require more explanation.
Okay, we have another really broad question. What is the difference between OSI and TCP/IP model, or just TCP model?
Very good.
Sorry.
That's a clear question and simple enough. It's just different ways of classifying the various functions. So OSI model classifies the various functions of the networking process into 7 layers. TCP/IP model divides it into 4 layers. Right. So for example, let me clarify. Again, I'll go back in the presentation just for a moment to give you a visual. So this is, by the way, the TCP/IP model. Notice if what OSI model calls layers 1 and 2, TCP/IP calls network access layer. What OSI model calls network layer, layer 3, is just called internet layer in TCP/IP. Transport is the same for both, layer 4. And TCP/IP model will lump the upper 3 layers, application, presentation, session, into one layer called application layer. Just a different way of classifying, same set of functions though. That's all. And just a different way of, representing it. Otherwise, the same idea. Yep.
Okay, move on with the next question is, does anything change, or how does it really matter when the world is moving towards IPv6 and 5G?
5G is a different can of worms altogether, but IPv6, by and large, a lot of what we spoke about today does not change. It's just that the TCP/IP suite changes a little bit, but the functions still remain the same. How it goes about performing those functions changes a little bit. That's why, in fact, even to understand IP version 6, having a good understanding of IP version 4 is still helpful. And most of the world is still using IP version 4. So, so 5G is a different can of worms. I, don't even want to talk about that right now. It's not going to relate as much to these things quite as much. Not quite. I mean, of course, it's going to give us the same set of functionality, right? Bear in mind. But with IPv6, the ideas will still remain fundamentally the same. Just the specifics of how it's done will change. Yeah.
Okay, thank you. Here's a simple one. What is supernetting?
Good question. Subnetting is the process of breaking up one larger network. Remember how we slice the pizza? Taking a larger pizza, making it into smaller slices. Supernetting is the equivalent of combining a bunch of slices into a larger pizza. So you take, not even slices, but how about combining a bunch of pizzas to make a larger one? I don't know, make a pizza sandwich, so to speak. So, and that may be a poor, somewhat confusing analogy, but the idea is to combine multiple networks to form a larger network. And it's not necessarily just done for the purpose of our regular networks. We sometimes use it to summarize our routes. If a large ISP owns lots of smaller networks, it's not going to tell another ISP. Like Verizon's not going to tell AT&T, hey, I own this network, I own this network, I own that network. It's going to combine those into one network and say, look, I own this whole block, which actually comprises of lots of networks. So that's called supernetting. And so it advertises that over to Verizon, will advertise that to AT&T, saying, look, don't worry about the details. To get to anything in this block, just send it to me, I'll take care of it. So that's one common use of what we call supernetting. It's also related to CIDR, classless inter-domain routing, where we disregard the class also then. And we don't care for the class at that point. But yeah, that's how you think about it. Yeah.
Thank you, Parag. Let's see. Can you explain NAT, network address translation, and how it works?
Okay. Very quick and a very high-level explanation. That's a little complicated as well, somewhat complicated. But the high-level explanation is this is literally what all our routers at home and routers, not most, but some of our routers at the office will do when basically we are trying to use the reason we perform NAT, or network address translation, is to allow us to use private addresses within our network, because otherwise the internet would have run out of addresses a long time ago. Right? We would all be on IP version 6 or IP version 8 or something else right now. But IP version 4, there are just not enough addresses. And as a result, what happens is we use what are called private addresses in our network. Those cannot be sent out. So then, well, you say, well, I still need to be able to get to the internet. It's no good having a private address in my own network. There's nothing interesting going on here. All the interesting stuff is out in the internet where you cannot use private. You have to use public addresses. And so a NAT is a process that translates, literally changes, switches the private address to a public one before the traffic is allowed out on the internet. All the ISPs are doing it. Our home routers are doing it. So that's what allows us to still continue using, IP version 4 addresses. Otherwise, yeah, we would have run out. So that's where it is. At a high level, the specific details is a little bit more involved. I'd have to break it out and draw some diagrams, and it would take more time. But it's not too complicated once you have a good understanding of some of the foundational information.
Thank you, Parag. I think we have time for one more question. Can you tell us what the basic difference between IPv4 and IPv6?
Sure. So, IPv4 is literally like half a century old almost, right? And it does not have enough addresses for, maybe even one country these days. Forget about the world. And when it was IP version 4 was designed, it was designed with functionality in mind. They weren't as concerned about security and a lot of the other stuff. They said, look, if this thing just works, it'll be great. That'll be good enough. Because back then, 50 years ago, think about it. I mean, we were in the technological doldrums, right? So that's what it was. Then eventually they realized, look, okay, this now, and it was originally designed for the U.S. Department of Defense only, right? Not for the whole world. They did not in their wildest dreams imagine the whole world would be using it. So that's why they didn't even think of coming up with more addresses at that time. I said, yeah, plenty. Who's going to use this? It was all like, only a bunch of mad scientists and a few special devices will use this, is what they thought. Well, eventually the whole world started using it, and then they had to come up with some much better plan, and IP version 6 was developed. But because it's a pain to migrate from 4 to 6, a lot of organizations haven't done it yet. And IP version 6 has a much larger address space, so you'll have a virtually infinite number of addresses. I mean, you and I can assign addresses to every thumbtack, every nail in the house, and we won't run out of IP addresses. And it's also got built-in security. It's got other functionality that is much more efficient, if you would. So those are the enhancements to IP version 6 that have been introduced and designed. And eventually we'll all either move to that or some other newer version of IP. But that's the key difference. But at the end of the day, they're still performing the same basic functions. There's still an IP packet, there's TCP and UDP and stuff like that, and there's, various other functions are still being performed. It's just being done differently. Security is built in, it's integrated, right? So that's one of the other enhancements. They've simplified the packet structure to make it more efficient for routers and other devices to process it and so on. So those are some of the key enhancements to IP version 6. But functionally, it's the same. So that's why it's also helpful and important to understand version 4 first. Makes it easier to actually even understand version 6.
Great, thanks, Parag. Yeah, we'll go ahead and get this finished up. Once again, thank you, Parag. It was a fantastic session, fantastic presentation. I hope everyone enjoyed today's webinar. If you'd like to learn more about this topic, we recommend our Understanding Networking Fundamentals course. We'll cover a lot of the topics that Parag discussed today. And in this time of social distancing, I would like to call out that this course and most of our courses are offered in virtual or on-demand formats, so you can continue to build your networking skills safely. And as an attendee of today's course, we'd like to help you take the next step. Use these discount codes to save 25% off your next Global Knowledge course. Use Webinar 25 in the US and CA Webinar 25 in Canada. Finally, be sure to continue to visit the Global Knowledge website to access additional free resources like technical articles, white papers, and other webinars. Thank you, stay safe, and have a great rest of your day. Thank you again, Parag. Thanks, everybody.